And good evening to everybody. It's nice that it's a Friday evening, so we can start winding down now. So obviously today I'm going to talk about the Webb Telescope. Oops. So myself, obviously Patricia's already introduced me, but I'm Dr. Stephen Wilkins, and I'm head of astronomy and a reader in astronomy at the University of Sussex, just outside Brighton. So I'm joining you today from actually the South Downs National Park, which is where I live. In addition to those roles, I'm also a public engagement fellow, which means I build exhibits and give lots of talks and things like that as well. So here is a nice artist visualization of the James Webb Space Telescope. Obviously, this is what we hope it will look like when it starts unfolding. And I'll show you lots more cool visuals of the telescope over the course of this evening's talk. And just apologies if there's any background noise. I've got two small children in the house who can never be quiet. Anybody who's got small children will know that no matter what you tell them, they're never quiet. Okay, so first of all, I'm going to do a very brief introduction to the telescope itself, and then kind of drift towards talking about some of the science. I'm going to mostly focus on the science today because I'm a scientist. So I'm not one of the engineers who's worked on building the telescope. I'm one of the people who's going to be using the telescope when it launches. So for anybody who doesn't know, the Webb Telescope or the James Webb Space Telescope or JWST is our next flagship astronomical observatory. It's actually the scientific successor to both Hubble and a much less known telescope called Spitzer. So here again is a nice little model of Webb. And what I think is quite striking about Webb here is that it doesn't really look like a traditional telescope, whereas perhaps Hubble and Spitzer did. And after many, many years of delays, people who are familiar with the project will know about this. The project has been delayed, depending how you count it, actually more than a decade now compared to when it was supposed to launch. But after all of these delays, we're fairly confident of a launch in mid to late December. Right now, this, as I was just saying, this could drift a little bit because of the weather, but all the signs are really good that this is going to happen imminently. And one of the other really important things about Webb is actually it's a collaboration. So it's a collaboration between NASA, the European Space Agency, which obviously includes us here in the UK, and the Canadian Space Agency. Okay, so all three space agencies are members of the consortium, have all contributed towards its development. And in addition to the three space agencies, there's also hundreds of universities and research institutes and thousands of individual scientists and industrial partners who have contributed or will use the telescope over its lifetime. So this is truly an international endeavor, okay, more so than I think any previous space telescope. So as I mentioned already, Webb is the scientific successor to both Hubble and Spitzer. Okay, so you can see Hubble and Spitzer to scale here. So this is Hubble over here, and this is Spitzer, much smaller. So Webb is almost 6 times larger than Hubble and about 50 times larger than Spitzer, right? So when you're talking about these numbers, you're talking about transformational science, right? So we're going to have a telescope which is much, much larger. So it's able to see further away, it's able to see more detail, able to see much sharper, clearer details as well. Okay, so you can just see the comparison between the three telescopes here. But also Webb has a range of other capabilities which differentiates it from Hubble and Spitzer. So for example, Webb has extensive spectroscopic capabilities. What this means is we can actually take the light from stars, galaxies, or planets, and we can split them up into their component wavelengths, much like a prism is doing here to sunlight. Now, what this allows us to do is study objects in much more detail than you would be able to with just imaging alone. And I'll touch upon some of the science which this enables later. But perhaps most importantly is that unlike Hubble, but actually like Spitzer, Webb is designed to observe the infrared. Okay, so unlike Spitzer, it's focused on the near and mid-infrared. So you can see Webb is over here, and it really kind of touches all the way from the visible. So it covers a little bit of the visible over here into what we call the near and mid-infrared, whereas Spitzer has overlapping capabilities, but extended further this way and didn't extend quite as far this way. So in terms of wavelength, Webb is not a one-to-one successor for either Hubble or Spitzer. It kind of sits somewhere in the middle. And I'll mention in a few moments why we care about the infrared. Okay, so that's what I'm going to come on to now. So why are we building an infrared space telescope? Why is it important that we do this? Well, first of all, infrared light is light beyond the red end of the electromagnetic spectrum. Okay, so it's just beyond where we can see with our own eyes. And it was actually discovered, like many things, accidentally by William Herschel more than 200 years ago. So you can see there's a picture of William Herschel over here. The reason why the infrared is only really now being probed in detail is because the Earth's atmosphere is actually opaque to most infrared light. So this little diagram here, this shows how opaque the atmosphere, how much of the light from space our atmosphere blocks as a function of the wavelength. So over here in the X-rays and the UV, the atmosphere blocks a lot of this light. That's really good for us because X-rays and UV light can be very damaging for us. And then we see the atmosphere becomes pretty transparent over here in the visible. This is why we can see things. And then as we go into the infrared, it gets a bit complicated, first of all, but then the atmosphere becomes very opaque. And so in these areas here, we need to use space observatories to get above the atmosphere to actually probe our universe. You can also see that the atmosphere becomes very transparent over here in the radio. And this is what allows us to enable all of our technology, things like Wi-Fi and mobile communications. So what causes the infrared? Well, like visible light, the most important mechanism for producing infrared light is just what we call the thermal motion of charged particles. So anything with a temperature produces light. Okay, so when we look at this steel rod here, this steel rod has been heated up to a very high temperature at one end, and the temperature is so high over here that it's emitting visible light. Down here, where the metal is cooler, it would actually be emitting infrared light. So we can kind of label this here. So very hot objects emit most of their light in the visible, whereas cool objects, we're going to emit most of their light in the infrared. Okay. So for example, people, and we've got a picture of one of my children here. So this is my daughter, as viewed using an infrared camera. And you can actually see in this infrared camera image, my daughter is actually glowing. So people produce infrared light because we have roughly the right temperature to produce infrared light. Now, you've probably seen this type of technology used before, maybe on police or crime programs, where people are chasing a criminal, for example. So this is quite good because people are generally warmer than their surroundings. And so if you kind of choose your bit of the infrared correctly, you can pick out the warm people from the cooler surroundings, or animals, or whatever you're looking for. But the infrared light is also produced by a variety of astrophysical phenomena as well. Okay, so I'm going to talk through some of the things that we can look at in the infrared. Well, first of all, just normal stars like the sun produce lots of particularly near-infrared light, as well as some visible light and some UV. So this image here is actually an image of the Milky Way. So this is just a portion of the Milky Way, but as viewed in the infrared. And it looks very similar to what you might see in the visible. And that's because this is actually into the near-infrared. So we can just expand this. Okay, so we see this really glorious view of tens of thousands of individual stars towards the center of the Milky Way. Okay, but this is now viewed in the infrared. So there are types of objects, for example, brown dwarfs, which are basically mini stars. In fact, they're actually too small to be real stars. These have temperatures below about 1,000 Kelvin. And they're so low in temperature, they actually emit most of their light in the infrared. So in fact, these brown dwarfs, if we looked at them with a visible telescope, we would barely see them at all. And it's only by looking at them in the infrared that we can actually see them. So there's one example of one of these brown dwarfs here. So this is the brown dwarf as viewed in the infrared by Hubble. Okay. And actually these brown dwarfs, they're somewhere between stars and planets in terms of their brightness and their characteristics. So for a long time, people were really interested in studying these as a precursor to studying planets. And so a lot of work went into studying these objects over the last couple of decades. Now, lots of people in that field are now transitioning to actually work on looking at planets instead, because we now have the capability to look at individual planets around other stars. And again, that's something that I'll touch upon again later. This is not an infrared image anymore. This is a visible light image. And when we look at things like the Milky Way in visible light, we often see structures like this, these big dark patches here. Now, these are not an absence of stars. This is actually where we've got clouds of gas and dust, which are absorbing the UV and visible light. But when they absorb that UV and visible light, what happens is they heat up and they actually re-emit that light in the infrared. So we can see this in another way here. Hopefully some people are familiar with this galaxy. This is the Andromeda galaxy. So this is our nearest major neighbor. You can see the Andromeda galaxy quite easily with a relatively small pair of binoculars. And if we look really carefully at this image, we can see there are these dark lanes in Andromeda. Okay, so we can see a few of them. Hopefully you can see the one with the arrow here. Now, at first glance, you might think this dark lane is due to the absence of stars. But if we, instead of looking at this galaxy in the visible like we're viewing here, if we look at it in the infrared, we see a very different picture. In fact, we almost see the opposite. So the areas that were previously dark, it turns out, are now bright. And that's because the areas that previously dark were not dark because of an absence of stars. They were dark because of this structure of gas and dust, which is absorbing all the visible light. Now that visible light gets absorbed, that energy has got to go somewhere, and it's re-emitted in the far infrared, which is what we're seeing here. Okay, so the kind of key point here is only by combining the visible and the infrared together do we really get the full holistic picture of what objects look like. Also turns out that kind of in between the far infrared, which I was just showing, and the visible, we have the near infrared. And in the near infrared, it turns out that you're not really seeing the dust glowing, but you're able to see through the dust. And this is because near infrared light basically doesn't get absorbed by the dust. So here's one of my favorite pictures in the entire universe. So this is the pillars of creation. This is a star-forming bit of our own galaxy. So this is where new stars are forming. And this is what it looks like in the visible over here on the left. Now, if we look in the near infrared now, we're actually able to see through most of this gas and dust and actually see the stars behind and inside this structure. So by looking in the near infrared, we're actually able to see through the dust, right? And this allows us to, for example, see where the stars are forming and the planets are forming. And then very similar to what I showed you before, if we look in the far infrared now, we almost see the opposite of what we see in the visible, but we actually see the dust glowing instead of being dark, okay? And it's really by putting these three images together that we can learn about structures like this, okay? So this particular structure here, this is where new planets and new stars are forming all the time. And if we only had the visible here, we get a very limited view of what's going on here. It's only by combining it with the near infrared and the far infrared that we're able to figure out what's going on. Okay. Another thing that we can use the infrared for is the fact that as light passes through material, for example, gas, that gas imprints its composition on the light through a series of unique absorption lines. So, for example, this. Over here, we've got sunlight. This is the spectrum of the sun as viewed through a very high resolution spectrograph. So what's happened here is that we've taken sunlight and we've been able to split it up into all of its individual component wavelengths. And when you're able to do this, you're able to see this huge collection of dark lines. If you look really closely, there are thousands of these lines. It turns out that every single line that you see there is associated with a particular transition in the elements in the sun's atmosphere. So actually by measuring the darkness of those lines and their location, we can actually figure out what the sun's atmosphere contains. So for example, this very dark line, this very dark broad line over here on the bottom right, this is actually the signature of hydrogen. right? So this tells us that the sun's atmosphere is actually mostly hydrogen, okay? But by actually studying these lines individually, we can work out exactly what the sun's atmosphere and therefore the rest of the sun contains. And we don't just have to do this on the sun, we can do this on any object now. As long as we've got a big enough telescope that we can do this type of spectroscopy, we can study objects in this kind of detail and actually work out what they contain. Okay, so measuring these absorption lines allows us to determine the properties of the gas, the stuff that we're seeing the light go through. And this includes its composition, but also things like its temperature and density. Now, the infrared, really importantly, contains features associated with not just elements, but actually molecules, things like water, methane, carbon dioxide, and ozone. So actually, by looking at objects in the infrared and using this same technique via spectroscopy, we can actually work out whether objects contain these molecules and others, right? And you can imagine some of these molecules like water and ozone are actually telling you something about the potential habitability of a planet, right, or another body. And so actually measuring these things is really, really exciting. Okay, so this is just making this point that infrared spectroscopy can be used to detect and measure the abundance of these molecules. And I'll talk more about this later when I talk about some of the specific science that Webb will enable. And then at the other end of the scale, the other reason why we care about the infrared is that since the mid-20th century, we've known that our universe is expanding. And a consequence of this is that the light from the most distant objects is stretched, it gets shifted to longer or redder wavelengths. Okay, so this is an idea called cosmological redshift, and it's a little bit similar to the Doppler effect for sound. So you know, as a police car or a fire engine goes past you, you can hear the pitch of the siren change. And it's a very similar idea. And actually, by measuring the redshift, we can actually work out the distance to objects, and we can actually work out from that how old the universe was when we're seeing them. Okay, and in fact, we can measure the redshift really easily by using these emission absorption lines that I was just telling you. Okay, and again, I'll come back to some more of the specific science in a few minutes, but I just wanted to kind of set up why we're interested in the infrared in the first place. So now I'm going to talk a little bit more about the spacecraft. So this is what Webb looks like. Okay, so we're seeing 4 different views of the Webb. I'm just going to highlight some of the individual features of Webb here. Okay, so we've got this large 6-meter diameter primary mirror. We've got a secondary mirror over here as well. So if we're looking at this top left-hand corner view, what happens is the light comes in from the left, it bounces off the primary mirror towards the secondary mirror, and then the light gets sent down through the primary mirror, so through the center here, right? And it ends up in the instrumentation suite, which we can see on the reverse picture on the bottom right. And that's what carries all of the cameras and spectrographs. And we can also see the other main feature of the telescope is the sun shield. And on the bottom of the telescope, we also see the power supply and the communication system. So one of the really clearly defining features of Webb is its very large mirror. And its mirror is actually made up of 18 of these individual hexagons here. So this is actually just one of the hexagons. This is actually a picture from several years ago now where they were testing the individual panels. Okay, and you can see here the individual mirrors are actually gold. And in fact, they are literally gold. So they're coated in a very thin layer of gold. And the reason for that, instead of using something like aluminium or steel, is that actually gold reflects infrared light much better than other materials. So gold is really the best reflector of infrared light that we have. And this is why the telescope has this color. Okay, whereas things like aluminium and silver and steel are very, very good reflectors of visible light. All right. Okay, so here is the telescope again. So this is quite a nice view of it. So what's happening here is the telescope has been assembled at this point, and it's been moved into this test chamber over here. So this test chamber here is specifically designed to mimic some of the conditions in outer space that Webb will experience. So I believe that this test chamber here, this one is a temperature test chamber. So this pulls down the temperature of the telescope down to the kind of temperature that we expect it will have in outer space, which is about minus 230 degrees below zero. Okay, so very, very cold. It's about the same temperature as Pluto. Okay, here's another view of the telescope. Again, you can see the primary mirror, but you might see that something looks like it's missing. So you can see in this view, we're actually missing the two wings of the primary mirror. And that's because these two wings are actually folded up. And it turns out the entire spacecraft actually has to fold up in order to fit onto the launcher. Again, this is something that I'll come back to a little bit later as well. Okay, so an observatory is really a combination of several different elements. So we have the telescope, the actual optics, but then we also have the instrumentation. Okay, so this includes things like the cameras and the spectrographs. So Webb actually has 4 science instruments. They all have actually unimaginative names. So one's called NIRCam, one's called NIRIS, one's called NIRSPEC. NIRCam and NIRSPEC stand for the near infrared camera and the near infrared spectrograph. And then there's MIRI, which is the mid infrared imager. MIRI is very close to our hearts here in the UK because it was actually co-led by the UK by Gillian Wright, who's a scientist up in Edinburgh. And actually much of the camera was actually built and tested here in the UK in various different sites. So this is really, really close to our heart here in the UK and just shows what type of contribution we're making to the overall project. This is all of the instruments now put together. This is very kind of difficult to see what's going on here in terms of the image because there's so much structure here. But what you're seeing here is basically all 4 cameras embedded into one kind of instrument suite, which then gets attached to the back of the spacecraft. Okay, so one of the other really noticeable features of Webb is the existence of its sun shield. So on the bottom of the telescope, we can see there's 5 very thin layers of material, and they're designed to keep Webb as cool as possible. Okay, the reason why the telescope needs to be as cool as possible is because it's looking in the infrared, and anything with even a few degrees above absolute zero is going to produce infrared light itself. So if you're trying to look at infrared light and the telescope is producing infrared light, that's just going to make it much more difficult. And so Webb actually has a couple of strategies for keeping cool. One of these is via its sun shield. Okay. Apologies for sneezing. One of them is via the sun shield, and the second one is via its orbit. In fact, it actually has 3. It also has other ways of keeping cool as well. So here's another view of Webb. Again, you can see the wings of the telescope have been folded up now. But what you can see in this image really nicely is the sun shield. And you can see that the sun shield, hopefully this is obvious here, is made from this very, very thin reflective material. I think the best way of kind of describing this material is if you've ever done a long distance run or you've ever gone camping, you might take one of these very thin plastic blankets with you that you put over you after you've done exercise or when you're very cold that reflects your heat back onto you. And it's very, very similar material. It's very flimsy. And this is one of the reasons why we have 5 layers to this material. But the other main reason, the other main way of keeping Webb cold is via its orbit. So unlike Hubble and many other telescopes, Webb doesn't orbit around the Earth. It actually orbits around the sun, and it orbits around the sun around 5 times further away from the Earth than the Moon is. So it orbits at a very special point called the second Earth-Sun Lagrange point. So what happens is that Webb basically manages to orbit in exactly 1 year, and so it always keeps the Earth and Moon between it and the Sun. Now, the reason why this is useful is the Earth and Moon and the Sun are 3 of the brightest objects in the sky. And so having them all in the same direction compared to the spacecraft allows Webb to actually point its sun shield in that direction all the time. So it's reflecting all of the bright things away from it. Okay, so all of the bright things are always kind of underneath the telescope. The other thing to note is that Webb will be launched from the European spaceport, which actually, funnily enough, turns out to be in South America, on one of these rockets here. So this obviously isn't the rocket that's going to launch Webb. This is a very similar rocket that launched a few years ago. And this is one of the Ariane 5 spacecraft. So this is another one of the contributions of the European Space Agency. So the European Space Agency has provided pretty much two of the instruments, so MIRI and NIRSPEC, and has also provided the launcher and the launch capabilities. Now, I've already alluded to this, but actually to fit onto this rocket, which is one of our largest, the entire telescope has to be folded up. And actually, once it's on its way to its final location, it will slowly deploy and unfold. And I'll show you a really terrifying video at the end of this happening. Okay, so what is the science that we can do with Webb? Well, the key thing here is actually the combination of Webb's larger mirror and its optimization to study the infrared actually make it 10 to 100 times more sensitive than its predecessors, and also able to obtain much sharper images. And as I've mentioned earlier, unlike Hubble and Spitzer, Webb also has these extensive spectroscopic capabilities. So we're talking about viewing the universe in 10 to 100 times more detail than we could before. Now, that's going to allow us to consider a whole range of different scientific questions. And so Webb's flexibility means that it's not designed to just do one thing. It's really designed to tackle a whole range of questions spanning astronomy and cosmology. So there is no way that I'm going to be able to talk about all of Webb's scientific objectives. So I'm just going to highlight a few, and I'm going to highlight them fairly superficially. So first of all, planetary systems and the origins of life. First of all, Webb will be able to observe some of the objects in our solar system. So it won't be able to observe anything closer to the sun than it. So it won't be able to observe the Earth, the Moon, Venus, Mercury, or the sun itself. But it will be able to observe the outer planets, including Mars. So things like Mars, Jupiter, Saturn. And then all the minor objects beyond. And so Webb here really complements other telescopes and even probes, providing infrared imaging of the planets and also spectroscopy. So here, for example, we have an image of Jupiter obtained by an infrared telescope on the ground. So what Webb will do will obtain images like this, but in much more detail and much more frequently. Right? And actually, by doing this, you're able to study these planets in a lot more detail. So you can see that this image is very, very different from what you might see in the visible. So in the visible, you do see these bands in Jupiter, which are different storm systems, but they're much less pronounced. So what you're really seeing here in the infrared is the areas of storms which are hotter than other areas. So these bright areas here, these are much warmer storms than the darker bands. And it's only really by looking in the infrared that we're able to see features like this. Going a little bit further away, Webb will also be able to directly observe planets orbiting other stars. So it won't just observe planets in the solar system, it will observe other planets around other stars. So we've been able to do this for about 10 years. So what you're seeing here is a little video of a relatively nearby star. And what we've done here is actually take away the light from the star, because the star is very bright. And when you subtract the light from the star, what you end up seeing in this system are these 4 dots, which over time, over several years, in fact, appear to be going around or orbiting this object. So in fact, these 4 dots here, these are all individual planets, and they're all quite massive planets in this case. Now, what Webb will do is allow us to see much closer to the star and see much smaller planets. So all of the planets we're seeing here are things like the same size as Jupiter, but actually further away from the parent star than Jupiter is. And this is really about as good as we can do at the moment. But with Webb, we're actually able to get to much smaller planets, much closer to the parent star. Okay, so we're talking about getting down to planets potentially the same mass as the Earth, potentially as close to a star where you can actually have liquid water on the surface. So it might be that Webb is actually able to observe planets which are potentially habitable. Okay, but Webb won't just be able to take images of these planets. Via spectroscopy, we might be able to determine what those planets' atmospheres actually contain. And this even potentially means discovering planets which are habitable or may even harbor life. The way this happens is we can take advantage of something called the transit method. So if we look at a star will look something like this. Now, if you have the right alignment, every now and then, a planet around that star, will pass between us and the star. And what this will do is it will cause the light from the star to dim slightly. Okay, so it's like a mini eclipse. And this is actually one of the main ways that we're able to discover planets around other stars at all. Wow. But what's even cooler is that when this happens, if the planet has an atmosphere, some of the light from that star has got to travel through the atmosphere. And as that light travels through the atmosphere imprints on that light, or on a tiny fraction of the light from the star, what that atmosphere contains. Okay. Now, as I mentioned earlier, in the near infrared, we can see the characteristics of things like water, carbon dioxide, methane, and ozone. Okay, so what happens is if we observe a star when these transits are going on, we're actually able to look for the signature of these molecules actually in the atmosphere of this planet. It seems ludicrously difficult for us to do this, but we're actually able to do this already, albeit only for really large stars and certain molecules. Now with Webb, we'll be able to push this down to much smaller planets. So again, approaching the size of the Earth, okay, and planets that are orbiting kind of stars like the sun as well. So moving further out again, I've mentioned this earlier before, we know that stars and planets often form enshrouded by dust and gas. So this actually makes studying their origins and how they form in the first place very, very difficult. But with infrared light, like Webb will observe, we're able to actually see through the surrounding dust and actually get a glimpse of the process of star formation. So this is one of Hubble's views. So this is, again, another region of star formation in the Milky Way. And looking in the infrared, as we're able to do on the right, you're able to see some of the individual stars forming. Now, Webb will do this so much better that you're actually able to zoom into these individual stars and actually see them forming from the gas in situ. But what about galaxies? So going further out still, going beyond the Milky Way. Well, I think one of the coolest features of the universe is the fact that due to the finite speed of light, that it takes light a certain amount of time to travel, as we look out into the universe, we're actually seeing the universe as it appeared in the past. So images like the Hubble Ultra Deep Field, of which I'm showing a portion of here, these actually contain galaxies stretching back over almost the entire history of the universe. And so analyzing images like these allows us to study the evolution of our universe, the evolution of galaxies over almost the entire history of the universe. Okay, so each one of these points of light here is a different galaxy containing billions or tens or hundreds of billions of individual stars. And some of these objects, for example, including this red one over here, is likely to be a very, very distant, galaxy that we're able to see. So what does Webb do for us here? Obviously, we've been able to do this type of science with Hubble, but with Webb, we're able to push this into the infrared or much further into the infrared. And this is important because of the effect of cosmological redshift. Okay, so cosmological redshift means that the light from the most distant galaxies that is emitted in the visible in the UV, it gets shifted into the infrared. So if we want to measure the visible light produced by the most distant galaxies in the universe, we really need to use something like Webb. Now, it's really important for us to do this because just looking at the visible light allows us to measure, for example, the amount of stars, when the stars formed, and learn a lot more about them. One of the other things that we'll be able to do with Webb that we haven't been able to do with Hubble is actually look at how the universe builds up heavy elements. So we know that virtually all of the elements beyond helium were created when stars die, okay? So often in events like supernovae. So what I'm showing you here is essentially the deaths of 4 stars, okay? So we've got a couple of planetary nebulae here. So this is what happens when a star like the sun reaches the end of its life. It basically sheds its outer layers, and those outer layers are enriched with heavy elements. So over a star's life, it will convert hydrogen and helium into heavier elements, things like carbon, nitrogen, oxygen, all the metals. And when very big stars die, so stars much more massive than the sun, they typically die in supernova explosions. And again, they leave something that looks kind of similar, but is also enriched with heavy elements in the same way. Okay, so what you're seeing here is the leftover remains of stars that have exploded, and those leftover remains contain all of these heavy elements. Now, this is really important because we know that the Big Bang only really created hydrogen and helium. And so we needed this process to happen a few times in order to allow the Earth to form, because we know the Earth is mostly made of heavy elements, okay, so more heavy than hydrogen and helium. But also thinking about ourselves, we know our own bodies are mostly heavy elements as well. So in fact, most of the atoms in your body were created during the explosions or the death throes of stars, many of which may have happened billions of years ago. If you want to learn more about this particular topic, I also gave a talk via Gresham College a couple of years ago about the origins of the elements. So you can find this online by just searching my name on the Gresham College website. Now, with Webb's spectroscopic capabilities, we'll actually be able to detect emission and absorption lines from all of these heavy elements that we're interested in, okay, as well as the lighter elements like hydrogen and helium. And this will actually allow us for the first time to trace the enrichment of the universe over almost its entire history. So we'll be able to look at distant galaxies and work out how many heavy elements they contain, right? And we can actually see over time those heavy elements being built up by successive generations of stars. Now, if we look far enough away, we're also going to start to see the very first stars and galaxies to form in the universe. But these galaxies are actually really faint. And again, due to the effects of cosmological redshift, they're only visible in the infrared. So the only way we can actually see these most distant, very first stars and galaxies is by using a telescope like Webb. And we think Webb is going to allow us to do this. So it's going to allow us to find examples of the very first stars and galaxies to form in our universe. What I'm showing you here in this image is just an image that we found via Hubble. And this is a pretty young galaxy. So this is a galaxy when the universe was only 400 million years old, right? And this galaxy looks very different from the galaxies that we see today. It's much more kind of chaotic and disordered. But with Webb, we'll be able to push this much further back. So see examples of the very first galaxies and stars to form, okay? And that's actually my area of science. So this is exactly what I work on. This is the bit that I'm really excited about. So I pretty much just said that bit. And then going beyond this, I think actually probably most exciting, however, are the things that we haven't yet anticipated. There's this very famous quote from Donald Rumsfeld. I won't read it out, but you might be familiar with it. And it's this idea that there exist unknown unknowns. So things that we don't yet know are out there that we might discover with Webb. And in fact, every time that we've looked at the universe more closely, we've discovered new mysteries. It almost seems like some kind of weird joke the universe is playing on astronomers. Because every time we build a new telescope to try and solve one particular question, that telescope ends up actually leading us to lots more questions. And so some good examples here are things like black holes, dark matter, and then dark energy, right? Every time we look more closely at the universe and think we're actually going to be able to solve something, we find these new mysteries. And these are not just details that we're finding. Things like dark matter and dark energy are incredibly important. In fact, it turns out that most of our universe is made of dark matter or dark energy. So they're not just details, right? They're big things. And so I think what's really exciting about something like Webb, because it's going to look at the universe in so much better detail than we've been able to look before, is that we might find something that we just haven't anticipated at all. And I think that for me is probably one of the most exciting things. Obviously, I'm really interested in answering some of the questions that I already know, right? But I'm also really excited to find things that we haven't even anticipated yet. Okay, so this brings me towards the end of my talk and onto the mission timeline. So after many, many years of delays, Webb is now anticipated to launch on the 18th of December. In fact, Webb has passed all of its tests, and only about a month ago, it actually arrived, in fact, exactly a month ago, it arrived at the European spaceport in French Guiana. So you can see this is the actual ship that's carrying Webb here. I think Webb is in one of these large containers. Okay, and so actually over the last month and over the next month, Webb is going to be integrated onto the Ariane 5 launcher. So we've got a couple more pictures here. So here is Webb being taken from the container ship down to the actual spaceport. So you can see it's being driven in this rather nice looking truck here. One thing I haven't mentioned is that the price tag of Webb at this point is about $10 billion. I can imagine this was a very stressful journey for the driver of this truck. And this is Webb after they've unloaded it. And you can see that it's in its folded up configuration here. So it's basically ready to be put onto the launcher now, right? And you can see what Webb does here. It's this, it's folded up so you can actually fit a very large telescope into a rocket. So although this is one of our largest rockets, Webb is very, very large as well. So what happens next? Well, after the launch in mid-December at some point, Webb will spend about a month traveling to its final location. So this, as you remember, is the L2 point, the second Lagrange point. And during this time, the telescope will slowly unfold over the entire month. And I'll show you a little video later of that unfolding. And then after that, we'll see that after the first 2 or 3 months, the instruments will be turned on. The reason why they're not turned on straight away is that we need the telescope to cool down, and it will take a while to cool down. Okay. And then after that, we'll start testing all of the instruments, make sure they're working as expected. And then after about 6 months, which I must admit is kind of a torturous amount of time to wait, we'll begin the first science observations. And so actually, we won't end up getting any of the kind of first nice images until after about 5 or 6 months after the launch. So there's going to be lots of waiting around for us to do, hoping that the telescope is going to be working properly. And so that brings me to the end. And so I'm going to end just here by showing you the deployment video. You can see up here the amount of time which has passed since launch, and you can see here the location of Webb.